Alrighty, let's just do one more example of this Kirchhoff analysis. So I've written the steps up here, and it seems like I tend to do steps 1 and 2 at the same time. I'm going to draw the arrows and label the arrows for my currents. So the first thing we could ask ourselves is, how many branches do we have here? Well, there's a branch right in the middle, right? That counts as one branch. Branches go between junctions, basically. So wherever you have junctions, where wires are coming together, where you imagine that there's solder, that's a junction. So because of that, not only is this a branch, but there's another branch. Here's another branch. Here's another branch. Here's another branch. So that's 1, 2, 3, 4, 5 branches so far. And then what's actually kind of cool is that you see this branch? How it goes through the 10 amp source, comes down into the ground, and then, well, it comes up out of the ground and goes through to here. That's all one branch, believe it or not. It goes through ground. It goes through the chassis of your car or whatever we're talking about here. Okay, so we had the 1, 2, 3, 4, 5. We have 6 branches. Wow, that's a lot of different currents, folks. 6 branches. So this ought to put our Kirchhoff's current law to the test, huh? So let's start labeling some stuff. Now, as far as currents go, I always look for my source first, and here's our source. It's a 10 amp source. It's kind of convenient that it's a 10 amp source because that tells me, oh, it's 10 amps. And because that's 10 amps, you know that you've got 10 amps coming into the ground, and that means you've got 10 amps coming back up out of the ground, and that means that we've got 10 amps flowing through that resistor. Pretty cool. So we got that current labeled. We actually knew what it was. I guess we don't have to solve for it. That's cool. Now, if I follow this 10 amp flow here, it comes to a junction right there, and it's going to have to split somehow or something. I'm going to guess that it actually does indeed split, and that some of it goes up and some of it goes down. So there's 2 currents, one going up, one going down. What's this one? I have no clue, so I'm going to have to call it X because I have no clue whatsoever. X, that's what X is for. Now this one, first of all, you don't want to say X because you don't. If you said that was X, that would be like saying that that this current and this current were the same, because X is only going to stand for one number, right? When you solve for X, you get one answer. So you can't say they're both X, because that would be like saying they're both the same, and they can't be the same because the resistances are different. It's a lot easier to go through a 3 ohm than it is to go through a 9 ohm, right? So the currents are certainly going to be different. So I labeled that X. So for now, I guess I could have to maybe label that a Y, except as soon as you write a Y down, take a look at this junction and say what goes in, what goes out, and let's see if maybe I don't have to use a Y. What goes in, what goes out? Coming into this junction, 10 amps. That's what goes in. That's the only thing going out. Going out of this junction is X and Y both. So notice I don't have to label this with a Y because I can rearrange this equation, subtract X on both sides, and say, well, the Y has to be the same as a 10 minus X, so why don't I just do that? I'll label this as a 10 minus X. 10 minus X. Cool. So it's kind of like 10 came in, 10 came in, I drain a little this way, what's left over? Well, if I have 10 bucks and I give you X, I've got that much left, right? 10, take away the X that I gave you. So that's just one way to look at it. That would be a little bit quicker than setting up the in equals out equation, but however you do it, if that's X, that's 10, then that's 10 minus X. Now what I'd like to do next is follow one of my flows, and I'd rather follow the simpler one, the one that just looks like an X. If I follow this one, I'm going to have 10 minus X showing up in my equation, so I'm going to try not to. So I'm going to follow this current here. Now the thing is, that reaches a junction. And then what happens? Well, I don't really know which way the current is going, but I'm just going to say that it's going this way. I'm just going to say that. It's just easier for me to think that way, that the x comes in and it splits in half, not in half exactly. Some goes one way, some goes the other. It's not exactly half, but it splits. And so, okay, now we're going to need a y. Let me see, we call that y. Now we definitely need a y. And I still have another one to label, and I guess I'm going to call that z for the moment. But before I leave it with a z, let's do that balance over here. In equals out. What's going in is x. What's going out is both y and z. So guess what? I can subtract y on both sides. And that tells me that instead of writing z, I don't need to write z, I can use my x and my y. Try to keep the number of variables down, you know. Try not to use too many letters, x, y, z, q, w, j, whatever. You know, because it's just going to make your life harder. Get this stuff out of the way. Don't really need it anymore, right? Oh, okay. Get that out of the way. Well, how are we doing on the currents? Not bad, except that we still haven't labeled a current going through that resistor. So, I don't know. I suppose I could draw it this way, or I could draw it this way, and I'm just looking at this 10 amps and thinking, well, shouldn't stuff kind of go to the right? So this is just a guess. That's all it is. It's just kind of a guess. I'm going to say that current's going this way. So how am I going to label this? Well, I could start with the z, but do I really need to use the z? Maybe I can use x and y instead. So what I'll do is I'll come back to this junction. Notice that these two flows come together and then they go out this way. So these two currents both come in. They have to add up and leave, right? What goes in must come out. And what's coming in here, what's coming in here is a 10, come on you, is a 10 minus x is coming in, and then the y is coming in. And that's got to be equal to what goes out. So going through the 7 ohm resistor, 10 minus x plus y. Now if you'd rather do a formal in equals out analysis, be my guest. 10 minus x comes in, y also comes in, out goes z. This used to be called z. So you notice that z is indeed 10 minus x plus y. Okay. And I believe that means that I've got all my currents labeled. Nifty difty. All the currents are labeled. Good. And notice again, I kind of did steps 1 and step 2 at the same time. I drew the arrows and I labeled the arrows with their currents using the in equals out Kirchhoff's current law. Next step is to get my pluses and minuses done. On a resistor, put the minus where the mouth is. On the resistor, put the minus where the mouth is. On the resistor, minus where the mouth is. On the resistor, minus where the mouth is. On the resistor, minus where the mouth is. All the way around. All those resistors get the minuses where the current enters. And this is not a resistor over here. This is a source. And you do sources differently. Sources are done differently from resistors. Sources, the minus goes where it wants to come out. I'm pumping the electrons out there. That's where I put the minus. That's where I put the plus. And while I'm here, why don't I just put a nice little script red V to remind me that this thing has a voltage across it, and we have no clue what it is. We just have to use a variable V. It's 10 amps, but if I knew the resistance, I suppose I could multiply 10 amps times the resistance, but I don't know that either. So it's just V. You just have to use a V. And now I've done step 3. Right. Cool. And that means it's time to walk in circles. How many unknowns we got to solve for? We've got to solve for an x at some point. We got to solve for a y at some point, and we're going to have to solve for this v at some point. Now save that for last. Don't go walking through that yet. Save that for last. Okay? Walk some other circles, in other words. So choices of loop. Choices of loop include, oh, I could walk around the left side, or I could walk around the right side, or I suppose I could walk around like that, Or I could start walking through ground and over here like this, except that that goes through there, and I don't want to go through there yet. But it's one of those paths I could take. Forgot where'd my script V go? Hey guys. Okay, so you know, you could, if you wanted to get fancy, you could go something like this. You know, as long as you have a closed circuit, that's closed loop. That's what counts. Although, again, I don't want to go through that yet, so we're not going to walk that loop just yet. So where do you want to start? Tell you what, I'm going to start over here. I'm going to start with, I'm going to have Ant-Man, oh, for heaven's sakes. I'm going to have Ant-Man start at the top here, and I'm going to have him walk around this left loop, and I'm going to wrap my equation down. So let me try to, because I'll have to shrink a little bit to do this, try to write an equation down here. So here's Ant-Man, and he's coming down. In fact, you know what? I'm going to have him with it. Yeah, what the hell? We'll go down. I see a minus on the way in. And now I have to look for volts. And remember, that's not volts and that's not volts, but you multiply them together to get volts, which is called Ohm's law, by the way. Current times resistance gives you the voltage. So minus 6y, spit out the other end, come around, come around, come around. Oh, see a plus on the way in, put a plus. Volts, well again, it's a resistor. You have to do this multiplication thing. 3 times the current is 10 minus x, goes in parentheses. Ant-Man comes out the other side, takes a corner, sees a minus going in, minus again. And here it's going to be 9 times x to get those volts. And then he's back where he started, so equals to 0. Well, it wasn't such a bad loop. Certainly felt like it was going to be worse. Let's distribute, get rid of these parentheses. 3 times 10 is 30, minus a 3x, minus a 9x, equals to 0. I like to do my x's first. So notice I got the minus 3x and the minus 9x makes a minus 12x. Then I'd put the minus 6y. Then I've got my plus 30 equals 0. And actually, to be a really nice standard form, I'm going to subtract 30 on both sides. That is a line or an equation in standard form. That's my official equation 1. I got that by walking through the left loop here. Well, gonna need another equation, right? So let's walk a different loop. This time, let's have Ant-Man walk around the right loop. So he's coming down this way, he sees a minus on the way in, minus. I need volts. For a resistor, you have to multiply the ohms times your current, x minus y. Comes out this way, takes a corner, sees a plus on the way in. I need the volts. Again, it's a resistor, so I have to multiply the 7 ohms times the current, 10 minus x plus y. Okay, he comes out this way, now he's coming up, he sees a plus on the way into this one, and it's going to be a 6y there, and then he's back where he started. He equals to 0. And now let's clean up this equation. So we got distributing negative 4x. Minus times minus is a plus 4y. Make sure you remember that. Plus, I got a 7 times 10 is a 70, minus a 7x, plus a 7y, plus a 6y, equals a 0. Lots of terms. They're all on the left side, so it's just a matter of combining like terms. I like to get my x's first. There's some, so I have a minus 11x. Get my y's next. There's some. What is that, 17y? 4 and 7 is 11 plus 17y. And then I got my plus 70 there. So my last step is to simply subtract the 70 on both sides. And now I have an equation 2. Cool. This equation has an x and a y. This equation has an x and a y. Together, we ought to be able to figure out the solution to this thing. So maybe I'll get out a different color here, maybe a bit darker blue. With this one. Yep, okay. And let's take these two equations. Let's just write one right on top of the other. It's easier to get a look at them that way. Common denominators aren't going to be that easy because I either have to look at the 11 and the 12, which means multiply 11 by 12, or I have to look at the 6 and the 17, which means multiply 6 by 17. Yeah. Okay, so what I'm going to do then, I think I'm going to go to a lighter blue, actually. I think I'll just make this this top one, I'm going to multiply the 12 by an 11, and the bottom one, I'm going to multiply the 11 by a 12. So 11 times 12 is 132, so I have negative 132x's. Actually, I want one of those to be a positive. So if I use a negative 11, this will work a little better. So negative 11 times negative 12 is a positive 132x. Negative 11 times negative 6 is a plus 66y. Negative 11 times negative 30 is a positive, I want to say 330, right? Sure. Bottom one, 12 times this is a negative 132x. 12 times 17 is, I don't know. It's 204. So that's 204y. And then 12 times negative 70 will be a negative 840. Notice we're ready to add our two equations together. The x terms are going to cancel. 204 and 66 makes a 270y. A negative 840 plus a 330 is making a negative 510. It is what it is. Okay, so divide both sides by 270 like this. Y is equal to a negative 510 divided by 270 is 1 point, and I've got 8 bar over it. So 888888888, which I'm going to, for 3 decimal places, that'll be a negative 1.889. That's my y, and as long as I'm down here, I might as well solve for x, right? So I think maybe I'll combine this equation with this equation, because it doesn't matter which one I plug it in, really. They're all good. They all give you the same answer. So negative 11x plus 17 times y. But wait, y is negative 1.889, and that equals a negative 70. So negative 11x minus. So what do I get here? I got 1.889 times a 17. I got 32.113 equals a negative 70. Okay, so I have to add the 32.113 to both sides. So I got a negative 11x over here, and let's see. I got a negative 37.887 over here. Finally, to get x by itself, I need to cancel that negative 11 off of it. Negative by negative is positive. 37.887 divided by 11, it comes out to be positive 3.444. Hey, I got 2 positive answers. Oh, no, I didn't. Y is negative. I'm sorry. So y was negative just means that wherever I drew my y current, I drew it backwards. Now, let's take these 2 answers here. X is this, y is this, and start filling in our table. X is 3.444. Where's X? X is over here. So I got 3.444 going through the 9 ohm resistor. Cool. Now, this current here going through the 3 ohm is supposed to be 10 minus X. So if I put a little note to myself, this is 10 minus X, then I go 10 minus the 3.444 is equal to 6.556. So I got my amps there. Now for the rest of these, well, here's Y. Let's use Y next. I got Y going through the 6 ohm. And what was Y again? Scroll down. Y was a negative 1.889. Negative 1.889 going through the 6 ohm. So again, since it's negative, I drew the flow coming down, but really it was going up. Oh, well, what are you going to do? What are you going to do? Now, that negative is important. Keep it with you. Don't just ignore it. You have to, you have to put it on your answers and stuff. But looking at this current, that current's going to be X minus Y. This is through the 4 ohm. X minus Y. And that's going to be 3.444 minus a negative 1.889. And so you end up with a 5.333. Make sure you caught that, okay? X was 3.444, and I subtracted a negative 1.889. That's what X minus Y is. You end up with 5.333. Okay, we're getting there. You know, as long as I'm over here, the 10 amp source has 10 amps going through it. Yep. And by the way, this 10 ohm resistor over here had 10 amps going through it. That was actually kind of a freebie. So the only current we haven't labeled yet is through the 7 ohm. Okay, a little bit of math to do here. This is supposed to be 10 minus x plus y. So that's 10 minus x, which is 3.444, plus y, which is negative 1.889. So what is this coming out to? Yeah, 4.667. Okay, 4.667. We've got all of our currents done. For the for the voltages, this is where you just kind of have a blast. You say 10 ohms times this makes 100 volts. 9 ohms times this makes, I don't know, 3.444 times 9 equals, that's making 30.996. 7 ohms times this, and you get the idea, multiplying all the way across. So 7 times the 4.667 is, we got 32.669 volts right about there. 6 ohms times that, 6 times 1.889, and it's negative, by the way, is a negative 11.334 volts. 4 ohm resistor, 4 times 5.333 is, we got a 21.332 volts over here. 3 ohm resistor, 3 times 6.556 is, we got a 19.668 volts over here. Boy, a lot of resistors in this one. And to finish, remember this this 10 amp source has a script V, right? You have to stop multiplying. It's not 10 times 10. That doesn't work that way because that's not a resistance. So you have to actually solve for the voltage drop across that thing, and that means you have to walk another loop. And so what I'm going to do is I'm going to have Ant-Man walk. He started here all the time. I'm going to have him walk like this, down through the ground and up like this. That's going to be his loop. So I'll call this Ant-Man's final walk. Victory leap, how about that? Ant-Man's victory leap. Starting up here, the first thing he sees is a minus on the way in. Look up the voltage across the 4 ohm. The voltage across the 4 ohm is a 5.333. Okay, you just look up your voltages now. Then he comes around and he sees a plus on the way in, and it's the script V. And then he comes around some more, he's going through the ground, nothing here, and then minus, over here now, minus, and the voltage across the 10 amp, you can look it up right here, it's 100. And then we come up through this resistor, minus on the way in, and across the 9 ohm we've got 3.444. So, we're back where we started, equals 0. So what we've got then is we have a whole bunch of negatives there, right? We got a 5.333 and a 100 and a 3.444. Those are all negative. So we've got a negative 108.777 plus the script V equals a 0. So if you just add that 108 to both sides, you got something like 108.777 volts. You can stuff that right there. Wow, we have reached the mountaintop. There it is. There she blows. Full Kirchhoff. Kirchhoff like we mean it. 2 equations, 2 unknowns even, and all kinds of stuff. So, whew. I hope you enjoyed this unit. It's a cool unit. You still got 2 more homework problems to do. You've got a little more enjoyment for yourself. Try to smile. That'll release endorphins. That'll make you remember better. It works. You don't even have to mean it. It works.